right, welcome to The Explainer. Today we're diving into a discovery that completely changed the world, unlocking a power source like nothing we'd ever seen before. We're talking about nuclear fission.
So let's just jump right in. To really get a sense of the scale here, look at this number, 1 million. What's that mean? Well, if you split just one uranium atom, you get about 1 million times more energy than burning one molecule of methane, natural gas. It's just a completely different league of energy. A leap so huge, it's almost impossible to wrap your head around.
Okay, so where does all this mind-blowing energy come from? This isn't your standard chemical reaction, like setting something on fire. Nope, this is a nuclear reaction. We're going right to the heart of the atom. So let's get into the mechanics of how you actually split one.
So what is nuclear fission, really? Well, at its most basic, you take a heavy atomic nucleus, think something like uranium, and it splits apart into smaller pieces. These are called fission products. But the really big deal, the game changer, is what else comes out of that split. A massive amount of energy, and, crucially, more neutrons.
Okay, now this is the really cool part. How physicists actually picture this happening. It's not what you might think, like a marble shattering into pieces. A better way to imagine it is like a wobbly drop of water. An incoming neutron hits it, and the whole nucleus starts to jiggle and deform. It stretches out into this kind of peanut shape, and the forces pushing it apart on either end get stronger than the forces holding it together. Until, snap, it splits right in two.
Remember those extra neutrons I mentioned? That is the whole secret sauce right there. The release of those neutrons is what makes this so powerful. It's what allows a single, tiny event, one atom splitting, to kick off a self-sustaining, sort of atomic fire. Let's dig into how that one little detail leads to the unstoppable chain reaction. So, here's a really important distinction you gotta understand. Not all heavy atoms are the same. You've got fissile materials, like uranium-235. Think of these as super easy to split. Even a slow, lazy neutron can hit it and cause fission. Then you have fissionable materials, like uranium-238. This stuff is tougher. It needs a really fast, high-energy neutron to make it split. Because U-235 is so much easier to work with, it's the go-to fuel for most nuclear reactors.
And check out this quote. This is physicist Leo Szilard, and it just shows how incredibly ahead of his time he was. In 1933, supposedly while waiting to cross a street in London, the whole idea of a chain reaction just clicked in his head. This was years before anyone had actually discovered fission in a lab. He saw the entire possibility in his mind's eye before the science even caught up. Just an amazing moment of insight. But for years, this incredible idea was just that, an idea. Purely theoretical. That is until the winter of 1938. A team in a lab in Berlin got a result from an experiment that made absolutely no sense. And it would force everyone to completely rethink what they knew about the atom.
And this is just a classic scientific detective story. So first, in 32, the neutron is discovered. Suddenly, scientists have a new way to poke at the atom's nucleus. A couple years later, Enrico Fermi does just that. He bombards uranium and gets really weird, confusing results. The big whodunit moment comes in late 1938 from two chemists, Otto Hahn and Fritz Strassmann. They find barium in their sample, which should be totally impossible. It's way too light. They were stumped. And that's when Lise Meitner and her nephew Otto Frisch figured it out. They realized the uranium nucleus wasn't just getting chipped, it was literally splitting apart. They even gave it the name, fission. So once the secret was out, the news just ripped through the physics community like wildfire. And think about the timing here. This is right on the brink of World War II. The possibility of a chain reaction wasn't just a cool science experiment anymore. The implications were huge and, frankly, absolutely terrifying. And almost overnight, this theoretical lab discovery turned into the Manhattan Project. I mean, we are talking about a secret program on a scale that is just hard to fathom. They built entire secret cities, like Oak Ridge and Hanford, just to produce the right kind of uranium and plutonium. It was this gigantic scientific and industrial machine all pointed at one single goal, to create an uncontrolled chain reaction, to build a bomb. And so, when the war ended, the world was suddenly faced with this new reality. Nuclear fission had opened up two very, very different doors for humanity. One led to creation, and the other to destruction. Okay, so this is the absolute key takeaway. The physics behind a nuclear power plant and a nuclear bomb is exactly the same.
The same process that can peacefully boil water to make electricity for a city is the same one that can level it. What's the difference? It's all about the rate of the reaction. In a power reactor, you want things perfectly balanced, what they call criticality. One fission causes exactly one more fission. It's a steady, controlled release of energy. But in a bomb, you want it to go supercritical. Each fission causes 2, then 4, then 8. It's an explosive, runaway chain reaction.
So this is the dual legacy we're left with from that discovery back in 1938. On the one hand, you have this incredible source of carbon-free power. I mean, hundreds of power plants around the world run on this stuff. But on the other hand, you have the terrifying power of nuclear weapons, a threat that never really goes away. And then there's the other problem. What do you do with all the radioactive waste that's left over? It's a challenge we're still trying to solve.
Which really leaves us with this massive question. One we're still struggling with all these decades later. A single scientific breakthrough gave us both near limitless power and a weapon of unimaginable destruction. How do you manage a legacy like that? It's a puzzle of science, of engineering, and of global politics. And it all started with one strange result in a lab.